All right, continuing on this second part of Module 18, I'm going to show you a few more, like I said, hodgepodge reactions. So this next one is very common for chemists to use when we have a functional group, in this case an alkene, and we want to get rid of it. So I'm starting here with an alkene, and I want to turn that into an alkane. Notice the language that I would use around this is I would say I'm reducing the alkene, because remember, for an alkene, the oxidation level would be 1, and an alkane, the oxidation level is 0. So this is a reduction. So this is a way to reduce an alkene to an alkane. So a couple of things here. Just like the last lecture where we saw oxymercuration, and we said the mercury sort of behaves like magic. Um, in this case, we're going to use another magic metal, uh, and that would be PD. Okay, this is palladium. This reaction also works with platinum, um, and it's mounted on carbon. So we would call this palladium on carbon or platinum on carbon. Um, these metal surfaces uh, can often catalyze reactions, and catalyze a whole range of reactions. You may have heard the term catalytic converter before. The catalytic converter is part of your car's exhaust system if you have a gas-powered car, um, that has these metal surfaces like palladium and platinum, where certain reactions will get catalyzed. It catalyzes the full combustion of the gasoline, so it takes some of the fuel fragments that didn't get burned, and converts them to carbon dioxide. It converts carbon monoxide to carbon dioxide. It also helps reduce the nitrogen oxides in your car exhaust. So it'll convert those back to oxygen and nitrogen. Um, so those catalytic converters contain some of these precious metals. That's why you may have heard catalytic converters are very expensive. And in some places, they'll even get stolen by being cut right off of your car, because thieves can get money for them. And it has to do with these metals that are precious, that uh, that are very valuable. Um, the good news for you is that you don't necessarily need to understand how these metals do what they do. So, like I said, you can treat them as magic. Um, this is not a reaction that you need to know a curved arrow mechanism for. What I want you to know about a reaction like this is that essentially you've got your metal surface and hydrogen, a hydrogen molecule, H2, kind of looks like this. It will come, float down to the surface, and it will connect itself to that surface where those two hydrogen atoms are held to the surface, and the bond between them um, gets weaker. So I'm going to draw it with a dotted line here. Um, so it connects to the surface, and then my alkene comes floating down, and essentially picks those two hydrogens up from that surface at the same time. That's going to make the alkene go from planar to tetrahedral on both sides. Um, so not a curved arrow mechanism. This is just sort of a cartoon of what's happening. Um, what this means is both hydrogens are getting added at the same time. Um, so that leads to a syn addition of the two hydrogens. So if I were to start with this cyclic alkene, the two hydrogens I would add would go the same way. So I could choose arbitrarily which way I'm going to have them come forward. That's usually my default. So my two hydrogens that I'm adding are both going to come forward. That would push the two methyl groups back. All right, so catalytic hydrogenation is something we use when we have an alkene and we'd like to get rid of it. Um, you could also use this with deuterium. So for instance, if I had just this cyclic alkene and I were to add D2 with my metal catalyst, remember D is just short for heavy hydrogen. So that behaves like hydrogen in all ways, except it's sort of marked. We can tell it apart from hydrogen. This would give me a syn addition, and it's a way to add some markers to my molecule. So that's catalytic hydrogenation. You don't really need to know anything more about it. You will see, if you take future organic chemistry classes, you'll see this set of reagents, H2 with palladium on carbon, a whole lot, because it turns out this palladium can catalyze a whole lot of different reactions where we're adding hydrogen to different molecules. All right, so that's a reduction of an alkene. What if I want to look at an oxidation? Okay. It turns out one useful reaction can be to turn an alkene into an epoxide. You might remember an epoxide is a molecule with a 3-membered ring with carbon. So this here is an epoxide. And it turns out we have a way that we can make an epoxide in one step. I'll show you in a future module how you can make an epoxide in 2 steps. But this is a nice, efficient way to make an epoxide in 1 step from an alkene. And it relies on the set of class of reagents called peroxy acids or peracids. So the most common that we use, because it happens to be relatively stable, is known as metachloroperoxybenzoic acid, or MCPBA. So you will see this reagent name MCPBA from time to time. Bottom line, with peroxy acids or any peroxide molecule that has that OO single bond, this is the key feature, is that we have an OO single bond. OO single bonds are relatively weak, and they tend to make for relatively reactive molecules. So OO molecules with OO bonds tend to be less stable. Household example, in your medicine cabinet, you might have a bottle of hydrogen peroxide. Hydrogen peroxide looks like this. It has an OO single bond, and that's always going to be sold in a usually brown light blocking bottle. And the reason is just ambient light often has enough energy to break that oxygen-oxygen single bond, and that will catalyze the decomposition of hydrogen peroxide. So that's why hydrogen peroxide generally comes in a brown bottle rather than a clear bottle. So we're going to take advantage of that oxygen-oxygen single bond. Turns out sigma star OO is a very good acceptor. And that's what we're usually taking advantage of whenever we use a peroxide molecule in a reaction. Although we'll see an example in the third part of Module 18 of a reaction where we break the OO bond in a different way. So this reaction where we react an alkene with MCPBA is going to follow a mechanism very similar to one we've seen before, where we form a three-membered ring, and that is the formation of the bromonium ion. So you might remember in that reaction, we had two things going on. We had the pi CC attacking sigma star BRBR, still my favorite orbital to say. Well, at the same time, we had the counterattack of the bromine lone pair attacking pi star CC. All right. So this is a reaction that you've seen before, and MCPBA is going to take advantage of a similar pattern in reactivity. So my peroxy acid generally looks like this, where I have carbon double bonded to oxygen. This is the key part of it. Carbon double bonded to oxygen, single bonded to oxygen, single bonded to another oxygen. I've just redrawn it below in a different geometry, and I took away the R group just for simplicity's sake. So when I take this peroxy acid functional group, the mechanism is going to be easier to understand if we first draw an alternate resonance structure. So this first step that I drew here is just resonance. So it's not actually anything happening. I just think the mechanism is easier to understand when we draw it from this alternate resonance structure. Remember, the actual structure is a hybrid of these different resonance structures to begin with, so we can choose any resonance structure we want and draw our mechanism from there. Just for practice, this first step would involve just sharing a lone pair here, moving that pi bond out onto oxygen. That gives us this alternate resonance structure. Now I'm going to use the alternate resonance structure in my mechanism. So I want you to look for the analogy here. Well, the good acceptor orbital, I've already said, is sigma star OO. It's a really great acceptor because both of those atoms are very electronegative. It's a very low energy sigma star. So I'm going to have my pi CC attack sigma star OO. That's going to break the oxygen-oxygen bond, just like we saw above with the formation of the bromonium. While at the same time, I'm going to have the oxygen lone pair attack pi star CC. Okay, so this is a reaction mechanism that looks a lot like one we've seen before. And you might be sitting there thinking, but there's something else going on at the same time. Well, at the same time, I also see that I have a new bond over here between oxygen and hydrogen. If you think about the structure of this per acid molecule, there was already a hydrogen bond between that oxygen and that hydrogen. Hydrogen bonding, something you learned about in your first chemistry class. You'll talk about them in biology. But there was already a hydrogen bond there. So what we're going to do is we're going to show, well, that hydrogen bond actually turning into a real bond. How does that happen? Well, the oxygen is going to share its lone pair with hydrogen, and that's going to break this bond here. So we do have a third interaction going on here where the lone pair on oxygen is donating to sigma star OH, and that transfers the hydrogen over to the other oxygen. That gives us our epoxide product. Is this a mechanism I would have expected you to predict? No, not at all. But it is a useful one, and I hope you can see the analogy to the prior mechanism where you formed a bromonium ion. Now, I will say I'm in the minority in terms of how I draw this reaction mechanism. Most chemists would draw this reaction mechanism as shown below. Um, they like this because it has an economy of arrows. It has fewer arrows. Um, and I don't think it really is as easy to understand because it doesn't have donor acceptor interactions that make a whole lot of sense to us. Um, but if you see someone else draw this mechanism, it will likely be drawn as shown down here with just 4 arrows, um, rather than having all the arrows that I drew to go to the alternate resonance structure and then to move the electrons in the reaction step. Um, Either one of those would be acceptable in my book, but uh, a lot of chemists would just draw it as shown here at the bottom. Just be aware of that. For you in this class, really the focus is knowing what you start with and what you end up with. So you start with an alkene, you end up with an epoxide. That's the key thing to note. One other thing, stereochemistry is kind of ignored here, but stereochemical relationships in my alkene would be preserved. So note that I started with a cis alkene. What that means is in the product, my 2 methyl groups here should be both pointed in the same direction. So that stereochemistry gets preserved. Um, this is a syn addition. We're only adding 1 atom, so essentially it has to be a syn addition. So if my 2 groups are on the same side of the double bond, they'll be on the same side in the epoxide as well. Um, all right, so we can, in this case, oxidize an alkene to an epoxide. One other addition that we often want to do is to turn an alkene into what we call a glycol, or a vicinal diol. So a diol is just any molecule with 2 alcohol groups. Break it down. Di means 2. All is my ending for alcohol or an OH group. So a diol has 2 OH groups. When there are neighboring carbons, I have introduced this word before, vicinal. Vicinal means on neighboring carbons. They could be called vicinal diols, or sometimes 1,2 diols, meaning you have one on carbon 1, one on carbon 2. And then a common name for these is glycols. I apologize on behalf of the chemistry community that we have to come up with so many different names for things. And I'm not telling you need to memorize all these names. What I am just introducing them for is that you might hear them from time to time and want you to recognize them. You might have heard of ethylene glycol, which is used in antifreeze, and that is just a 2-carbon glycol. So it's 2 carbons with 2 OH groups. So one way to make a glycol is to start with an alkene and then add the 2 OH groups. That can be done in 2 steps. First, you can turn your alkene into an epoxide. And then later on in Module 25, I'll show you how you can open the epoxide and turn it into 2 alcohol groups. So this would be your glycol. So I can turn an alkene into a glycol that way. There are also some reagents that would turn an alkene directly into a glycol. Osmium tetroxide is a fun one just because when else do you have the opportunity to use osmium? You might never have even encountered it before in your chemistry journey. But osmium tetroxide can be used to make a glycol. Usually there's a second step, a workup step, that involves a mild reducing agent. This is how it's commonly written. First step, OSO4. Second step would be something with the hydrogen sulfide ion. You can also accomplish this with potassium permanganate, KMNO4. So those are just a couple examples. One thing to note, these two have different stereochemical results. So anti-stereochemistry in the first case, where one is coming forward, one's going back. Syn stereochemistry in the second case. Um, Again, not reactions you need to understand mechanisms for, just reactions that you're likely to see and that would be synthetically useful to a chemist. All right, and one more reaction for our hodgepodge today. And this one's completely different. We've been looking at addition reactions where we take an alkene and we add something to both carbons. This next one, ozonolysis, is a way to actually break up a molecule into smaller bits. We don't do this a whole lot because usually chemists are focused on building up bigger molecules, but sometimes it can be helpful to break a specific carbon-carbon bond. And we can do that through what we call ozonolysis. So ozonolysis is a process where we react. Again, it's a two-step process like a number of the reactions we've seen, where we react with ozone in the first step. Ozone looks like this. Ozone looks like this. It's a molecule that's found in the stratosphere, and when it's up there, it's helpful to us because it absorbs UV light. Ozone, however, is quite reactive, and so when we find it down closer to surface level, it's actually really dangerous for us. It's a component of smog. When we have bad air quality, a lot of times that's caused by excessive ozone near the surface. If you look at weather forecasts, a lot of times they'll have a page for air quality, and they might list the ozone level for that day. Ozone's very reactive, and it turns out when it encounters double bonds, carbon-carbon double bonds, it can break them up. So that's one of the ways it can have negative interactions with us because we are made of organic molecules. So notice in this sequence, I'm starting with an alkene, and my products, in this case, are a ketone and an aldehyde. All right. When you break up an alkene using this sequence, it's going to make ketones or aldehydes on each side, depending on what you start with. So notice I started with a hydrogen on one side of my alkene. That side became an aldehyde. The other side had just two carbons, so that became a ketone. So really, whatever is already on your alkene gets preserved. So your products, you're always going to start with an alkene, and you could get two aldehydes. You could get two ketones, or you could get one aldehyde and one ketone, depending on what your starting alkene looks like. I'm not going to show you the mechanism for this reaction, so you can think of this sort of like a magic reaction. So step one, use magic scissors. All right, that's our first step. Use magic scissors to break that bond. Step two, is add oxygen. So that would be adding an oxygen here and adding an oxygen there. And step three, you don't really need to do, but generally aldehydes we draw in the hydrogen. On an alkene, it's not typical to draw in the hydrogen, but on an aldehyde, it is typical to draw in the hydrogen. So I'm going to add the hydrogen right there explicitly. If you didn't, it would be okay. People could interpret it, but it's just our convention to draw in that hydrogen. So take a minute, use that process to predict the products of these two reactions. And I will tell you, numbering carbons can be really helpful in this process. So pause the video, draw your products, and then come back. All right, so notice I numbered my carbons. When I split this up, I renumbered my carbons to make sure I kept track of them all. Hopefully you were able to come up with these two products for this first case. What about this second case? Now, when I break my carbon-carbon double bond, I'm not making two separate molecules. So I might initially draw it this way: 1, 2, 3, 4, 5, 6. I use my magic scissors and I separate those two, and then I'm going to add an oxygen on either end. I could draw my product this way. I also might redraw it just in a straight line: 1, 2, 3, 4, 5, 6. And if I did it that way, then carbon 1 has an aldehyde and carbon 5 has a ketone. So I could redraw it in a way that would just be a more conventional way to draw it. Either one of those is acceptable. If you were going backwards, if you were given the product and trying to predict what the starting material looked like, you would want to be able to take this molecule in this more linear representation and fold it back up to remake the starting material. So that's the idea with ozonolysis. Now, it turns out with ozonolysis, we can do two different kinds of second steps. One step would produce an aldehyde. That would be this one, where we use dimethyl sulfide as a second step. We could also follow up ozonolysis with hydrogen peroxide, which is further oxidizing. And when we do that, it gives us a little different result. So in this case, we start with an alkene again. Depending on our starting material, we might make a ketone, and we also might make this other functional group, which we call carboxylic acid. So what's different here is anywhere that would have been an aldehyde now becomes a carboxylic acid. So we're taking our alkene and we're either making two ketones, two carboxylic acids, or one of each. Depending on our starting material. So in this first example, we're making one of each. So go ahead and do the same prediction you did before, but now with the H2O2 as the second step. Pause, draw them in, and then you can come back. All right, to make my life easier, I just copied my work from the previous page. Um, and now I just need to make one change to my products, and that is wherever I see an aldehyde, turn it into a carboxylic acid. So in my first case, I have a ketone and an aldehyde. I'm going to just change that aldehyde to a carboxylic acid. In the second case, again, I have a ketone and an aldehyde. I'm going to change that aldehyde to a carboxylic acid. Other than that, everything stays the same. So that's ozonolysis. It gives you the option of doing what we call a reductive workup or an oxidative workup. We can end with an aldehyde or end with a carboxylic acid, depending on what reagent we use. This last one is asking you to work in reverse. Um, think about what the starting material would have looked like that gave us these three products. Again, I'd ask you to number your carbons, pause, see if you can draw the product, and then come back and check in. All right, hopefully you didn't have too much trouble with this. Essentially, when we do this in reverse, what we're going to do is take these carbonyl groups and glue them together. So instead of using magic scissors, now we're using magic glue to effectively glue carbons together and get rid of the oxygens. So we're going to glue them and remove the oxygen. The other thing we're going to do is we're going to replace these OHs from the carboxylic acid. Those would go back to just being hydrogens. So if I draw out my carbons, 3, 4, 5, 6, 7, I'm going to glue carbon 2 to carbon 4. So now I'll have a double bond here. That'll be carbon 2. Carbon 2 still bonded to carbon 1. And I'm going to glue carbon 8 to carbon 6. And then if I want, I can explicitly draw in the hydrogens here. I don't need to. They could be implied. But this would be my starting material. That would, if I did ozonolysis with H2O2 as the second step, would give me these three products. All right, great. So I know this piece of Module 18 was really a hodgepodge 3 or 4 completely different kinds of reactions. Focus on knowing what you start with, what reagents you use, and what you end up with. That's what you're going to have to do on the skill builder.